Okay, so let's start with a refresher. First weeks, we looked at forces, all right? Remember when we have a block and the force is applied to it, a force F, okay? That means that this block, first of all, will have also a weight, always going downwards. And if it's on a flat surface, it's also going to have a normal force going upwards, okay? This weight is equal to mg, which is mass times gravity. The normal force is just the reaction force to mg when there's no motion and acceleration, if you remember. If there's no movement up and down or no other forces, then n is going to be equal to w directly. And this force here is going to be to cause an acceleration in this direction. There's going to be an acceleration where the formula is F is equal to ma, where m is the mass of the object. All right, guys should have remembered this from the previous session. This is just a refresher. Then we looked over moments. Moments is when you have, for example, a beam or a cantilever beam or a seesaw or anything that is supported at one end, and then there's going to be a force applied perpendicular to that beam. So let's say this is the force F is being applied to it. This is, let's call it point O, all right? And then we have the distance from here to the force itself. This is what we call the perpendicular distance. Okay? So moment is basically going to be the moment about O, so the moment that is rotating around O is equal to the force times the perpendicular distance, okay? This is simple. We did a lot of examples with this. The most important thing is knowing the direction. So since the force is going downwards, we're just going to draw a line going towards O. This is how you will know the direction. So in this case, the direction is going clockwise. All right? And usually clockwise would be positive and counterclockwise would be negative, all right? Depending on how you assume your directions. Remember, when it comes to directions, you guys should be assuming up to whatever you guys are comfortable with. Usually, I always go with clockwise positive for moments, and I usually go for this to be my positive x and y direction. So this is plus y and this is plus x, okay? These are just the standards or the normal way of doing it. You guys can assume the opposite directions as well. There's nothing wrong with that. Just make sure that you are consistent with your assumption. Do not change the directions while solving midway. From the very beginning, assume a positive direction, and anything that is in that direction will be positive. Anything opposite to that direction will be negative. All right? So this was just a review for what we did earlier. Today we're going to talk about friction forces. So friction هو الاحتكاك. زين يعني when you have something flowing on a table, or if you're looking at the same example over here. This example over here, we had a force that is applied to a specific direction. زين, and it's on a table. All right. So in this case here, we usually assume that this is a smooth surface. A smooth surface basically means there is no friction. All right, there's no friction force holding it back. Yani this surface is very smooth. It will not be stopping your motion. In reality, we have an additional force called the friction force, and this friction force is always acting opposite. Okay, I usually call it FR. This friction force is always acting opposite to where your motion is. So FR. Hello everyone. I'm just adding this extra part for friction because there was an issue with the recording of the session. So when we were talking about friction forces, what is friction force? Friction is basically الاحتكاك, or the friction is when there is two objects like colliding with each other at two surfaces. All right. So let's say, for example, we have this surface over here. Okay. We usually know that there's going to be a force that is being applied in this direction. Let's call this a force F. And we know already that there's going to be a weight that is acting downwards, W. And we're going to know that there's a normal force that is acting upwards, normal force N. The friction force will always be trying to resist motion. So let's say that there's going to be a motion in this direction. Okay. So the friction force here is always going to be applied opposite to where the motion is available, or the motion is trying to go to. Yani when this force is being applied, this motion is going to be to the right, or expected to go to the right, if this force is high enough to overcome this friction force. So this friction force is basically just the resistance to motion based on the type of surface you have. And the friction force is equal to mu times n. And mu will be clarified later on in this video. Fr, and n is the normal force, as you know. Fr is basically the force, the friction force, and always opposite to motion. All right. And one more thing I want to talk about Fr is if we have a friction force over here, you notice that it always will make a 90 degrees with the normal force. This is always going to be the case because the friction force is being applied onto a surface or between the surface and the object, whereas the normal force is always going to be perpendicular to that surface. So there is always going to be a 90 degrees between your normal force and friction force. So the idea of solving for friction is usually determining what your normal force is. After you determine your normal force, you're going to multiply it with your coefficient of friction, which will be explained later on, and then you can determine your friction force. Is equal to W unless it's a specific case where there's motion up and down, which we talked about also last session. So you will try to determine your N, and once you know your N, you're going to multiply it with your mu. So what is mu? Mu is the friction coefficient, all right? And there are two types of mu's, which we will talk about, okay? So it is usually called the coefficient of friction. So this is the coefficient of friction, okay? And it's unitless. What does that mean? معناته it doesn't have any units. It's not meters, it's not kilometers, it's nothing like that. It is just unitless. It has no unit at all with it. So this will show us that if we have our force N, our normal force N is going to be in newtons. So our friction force will also be in newtons because they have to be dimensionally equal, right? So you cannot have two different units left and right. Since this is unitless, it will not add any extra units to the force. Like the example here, moment, if you remember, this is in newtons and the distance is in meters. So the moment is going to be Newton meters or Newton times meters, all right? In this case here, mu has no unit at all. So when you're multiplying it with the normal force, it's just going to be in newtons for normal force. So the friction force is also going to be in newtons. So mu is a constant. It's not a specific like way to calculate or anything. The actual, in reality, mu, it depends on the material of the surface. Okay. يعني if the surface is a rough surface, or يعني if it's made of steel, if it's made of wood, all of those have a specific mu that has been experimentally determined يعني a while ago, and they are going to be constants depending on the type of surface. And there are two types of mu. We have the first one that is called mu s. This is known as the coefficient of static friction. What does that mean? That means there is no motion. Okay? There's no motion. Basically, in other words, there is no acceleration. Acceleration is equal to 0. This is what this means. This is when you will use mu s. So mu s is when basically you are pushing this object. يعني the easiest example I usually explain with is if you have your calculator in your hand, you put it on your hand, okay, flat on your hand. And if you put a very small force at the back and you try to push it, it's not going to move. you will feel يعني on your other hand that's holding the calculator that it wants to move, but your hand is kind of stopping it. This is because of the friction force that is on your hand. It is larger than the force that you are applying with your finger. Okay, so if you're trying to push your calculator with your finger, you're going to notice it's not moving. When you apply enough force, if you put a lot of force on it, you will notice that it starts moving. So before it moving, like if it's not moving and you're putting your finger force on it, you will be using this mu s because there is no motion. This is how you will be able to calculate your friction force. All right. So this mu is going to be mu s. Then there's the other mu, which is mu k. Mu k. This is the same thing, the coefficient of kinetic friction. This is basically when there is motion. All right, so there is motion. In other words, there is an acceleration in a specific direction. Acceleration is not equal to 0. Okay, so these are the two different types of the friction coefficients. There's the coefficient of static when there's no motion, and then there is the coefficient of kinetic friction when there is a motion. So the static friction, basically, it keeps the object in place due to the friction force. Yani it is not moving due to the friction force being so high. And we're going to look at an example of that. Then there is mu k that is going to be taken into consideration when it's trying to slow down an object. So the object is already moving, but the friction force is slowing it down only. It is not letting it slide very freely. That is when you will be using mu k. So mu s will be used when the object is not moving, and mu k will be used when the object is moving. And this is the basics of friction. It's very straightforward. So just a quick recap. Friction is the force that will be opposite to the motion all the time. Friction, the equation for it is going to be mu times n, where mu is the coefficient of friction and n is the normal force n over here. And the coefficient of friction is two cases. One where there is no motion at all, so it is going to be called the static friction, the coefficient of static friction. And one where there is motion, and this is the friction force is only slowing it down. So it is going to be mu k, which is the coefficient of kinetic friction. All right. So if we look at an example, a very simple example, the same example, if we have a box, okay, on a flat surface, and then let's say we have this box, and this box is moving at a specific, with a specific force into this direction, okay? Yeah, okay. So it's moving with a specific force into this direction, a force F, all right? Actually, I'm going to keep my force F in blue so that there's no confusion. This is just the normal force F. Force F. I'm always going to use a green for my normal force. Normal force is going to be always upwards from the surface. And then I'm going to use purple for my weight. There's going to be a weight force. And remember, W is equal to mg always, where m is the mass and g is the acceleration due to gravity, which is 9.8 usually, or in the question it will mention it. And obviously the mass is the mass of the box. So now we will have a friction force. All right, we're going to have a friction force in the opposite direction in this way. Okay. So my question to you would be, let's give numbers. So let's say the mass of this is 15 kgs. All right, so let's say m is equal to 15 kgs. And the force is 63 newtons. Okay. So using this, we can already start determining everything. So the first step here you will do is you're going to do your sigma Fy is equal to 0. First of all, assume our positive directions so that there's no confusion. This is our plus y, and this is our plus x. So anything in the upwards direction is positive and downwards is negative. Anything to the right is positive and to the left is negative. All right? So sigma Fy is equal to 0. So this is because there's no motion up and down. There's no acceleration. It is equal to 0. All right? So we can find out that sigma Fy is also equal to the sum of forces. So n is in the positive direction. So it's going to be positive n. All right? minus W, because W is in the going downwards, so it's negative. And this is equal to 0, okay? Because sigma Fy, all the acceleration up and down is equal to 0. Because remember, F is equal to mass times acceleration. So if there's no acceleration up and down, the acceleration is going to be equal to 0. So F is going to be equal to 0. So the total sigma forces, basically all of the forces up and down, is equal to 0. This is how we got this equation. We know that W, before solving this equation, is equal to mg, which is equal to 15 times, let's say gravity is 9.81, all right? Again, gravity will be given to you in the question, so don't get too confused. It might be given as 9.8, as 9.81, as 10. Don't worry too much about that. So if we just multiply these, we're going to get 147.15 newtons, all right? So this is our W. We found our W. So if we just plug this back into that equation, so plus N minus W, what's our W? It is 147.15 is going to be equal to 0. So in other words, okay, if we just take this to the other side, we can find that N is going to be equal to 147.15. Since it's minus here, it becomes plus here, newtons. So we found our normal force N. Now we can find that, find out our FR, our friction force, using this equation. FR is equal to mu times N, all right? So I didn't mention the mu here. Obviously, mu will also be given. Mu S is equal to 0.58, and mu K is equal to 0.35. Okay, remember, these are unitless. They have no units. Okay, so mu S is the static friction, so when there's no motion, and mu K is 0.35. All right? So, my question here to you guys, first of all, before I move on, just if you notice, mu S is larger than mu K. All right, this will always be the scenario. Your static friction coefficient will always be larger than your kinetic friction. All right, the idea behind this is that when there is a body that's already in motion, the friction force is going to be a little bit smaller because of the momentum of the object moving forward. And then don't confuse yourself too much with this, but the static friction is always going to be larger than your kinetic friction. Now, so we found our mu S and mu K. Okay, I never said if this object is moving or not, but let's find out if it's moving or not. How can we check this? So the first thing we need to know is, we know that sigma Fx is equal to our force F minus our friction force, right? This is what we know. We know that the force F minus the friction force. Remember that friction is always going to be opposite to where the object is moving towards. But if there's no motion, friction will not pull the object to the left. All right, so friction is not going to pull the object to the left. Friction is only a reaction of when the object is already moving or trying to move in a specific direction. So what we need to understand is whether this force F is large enough so that it can overcome this friction, or if it is not large enough to overcome this friction. بما معنى إذا عندنا إحنا هني الفورس اذا احنا نستخدم نفس فكره الكالكوليتر، اذا قاعدين نحاول ندز الاوبجكت، زين اذا قاعدين نحاول ندزه، نبغى نعرف اذا بيتحرك على يدنا الكالكوليتر ولا لا. زين للحين في فورس بس مستحيل يروح اتجاه العكس. Alright, so the same thing, the same example with the calculator. If you're trying to push the calculator off your hand, it will never go in the opposite direction. And no matter how much of a force you put, large or big, it will never go up opposite to the force you're trying to apply to it. So the friction force is always either going to hold it in place, or it is going to be, the force is going to be large enough for it to move in the opposite direction. So we know that the force minus the friction force is equal to the total force. So let's look at this. So let's look at just the force F. F is equal to 63, was it? Did I say 63? Yes, 63 newtons. So let's look at our friction of static. So Fr is going to be equal to mu s times n. Let's find that. So we know that mu s, we already know it is given to us. Mu s, the static, is 0.58. All right, times the normal force we already have found to be 147.15. Okay? We will notice that our friction force, if we just plug this into the calculator, is equal to 147.15 times 0.58. It is going to be 85.347 newtons. If you notice, if we compare this force to the force that is being applied, the friction force is larger than our force. So basically, this force is smaller than this friction force over here, opposing the object. In other words, friction here is larger than a force. بما معنى there isn't enough force for this object to start moving, to overcome the static friction. فمعناته there is no motion. A is equal to 0. يعني this force is not moving the object because the friction force is too high. And this friction force depends on the weight of the object because of the normal force. And it depends on your coefficient of the surface that you are dealing with. So this is how you will determine whether or not this friction force is causing if this force, I mean, is overcoming the friction force and causing motion or not. If you notice here from sigma of x, if we plug in these values, it's going to be 63 minus 85, and we're going to get a negative number. All right, because we're getting a negative number, minus 22, معناته that the direction of all the forces is to the left. So the direction of the full force is going towards the left side. So it cannot cause motion because remember, friction force does not cause any motion. It is opposing motion. It is always slowing down or not letting the object move. So there is no motion to the left, obviously, due to friction. But there's also no motion to the right because the force F is not large enough. Does this make sense? Anyone has any questions about friction before we start solving more problems? I'm going to be solving now actual problems with friction. So you're going to be just a quick recap. The first thing you're going to do is you're going to determine your normal force using your sigma of y equal to 0. The normal force will be based on the weight of the object, and then most of the time, remember, there is a case where normal is not equal to weight that we talked about last time, and then but I haven't seen such questions in friction so far. But in general, you guys should already know how to get your normal force no matter the situation. Using sigma Fy, we find our normal force. Once we find our normal force, we can find our friction force as long as we are given either mu s or mu k. Mu s will be used when there is no motion for the object or to check if there is motion or not, like the way we did it for this question. And mu k is used for when there is motion. So in other words, if we have determined that acceleration is already present, okay, if we already know that acceleration is already present in this question, we will know that mu k is the one we are going to use because there's already motion. And then, but here I did not give you guys any acceleration. Here I gave you guys just the force, and I asked if there is acceleration or not. Tamam? So if there's no motion, you'll use mu s, or if you want to check for motion, use mu s. If there is motion, you'll use mu k. In this case, we don't have motion, or we're trying to check for it. So we're going to use Fr is equal to mu s times n. We found our normal force. We are given mu s. We found our friction force using sigma fx. Then using sigma fx, we're going to see if the friction force is larger or less than the force that has been applied. Since F is equal to 63 newtons, which is less than the friction force, we know that there is no motion. So we need a minimum force of 85.347 so that this object will start moving. Let us solve an example, a question. Let's see. Just 1 second. So let's start with this question. A 2-ton grinder is pulled along a horizontal floor by a winch. All right. So from the very beginning, we know that we have a floor. All right. We have a grinder that we're going to just put as a box. All right. And it's 2 tons. So we know that the mass is equal to 2 ton. Remember that 1 ton is equal to 1,000 kilograms. So 2 tons is going to be equal to 2,000 kilograms. Remember that you have to always convert your units to the correct units, the standard units, the standard international units, so that you can solve. All right? By a winch. So we know that this grinder is being pulled. So let's assume that it is being pulled in this direction to the right. So this is our force F. The coefficient of friction between the grinder and the floor is 0.35. So see, in this case, they just say that mu is equal to 0.35. It doesn't matter whether it's static or kinetic. Why? Because there's already a tension force being applied, and they're already just giving you mu directly. So you know this is the coefficient of friction that you're going to be used. So don't worry if it's static or kinetic in this case. And then, what is the tension in the horizontal rope between the grinder and the winch? So we need to find out the force F over here, what it's equal to. So we need to know what F is equal to. What is the tension in the horizontal rope? So tension is basically, if there's a line, so instead of calling it F, let's call it T so that there is no confusion. So the tension force T is basically how much the rope is being pulled out, how much force is being applied to the rope. That is what tension is. So we're going to have, first things first, we know that our friction force is going to be opposite to where the tension force is being applied. How do we know? Because we know that the girder is being pulled along. So since we know it's being pulled, that means this says that there is pulled. That means there is motion. Okay? So we know that there is motion in this direction, a specific acceleration, but we don't know what it is. All right? Then we have our weight, which is straight down, W, which is equal to mg, which we can already find. And then we have our normal force, which is from the surface going upwards. Tamam? See, the first step is always, when solving a question like this, draw your free body diagram so that you understand where the force directions are all going towards. And this is our friction force over here. So the first step is we can find our W. W is equal to mg. Mass is 2,000 kilograms. Gravity is 9.81. All right, times 9.81. So W is going to be equal to 2,000 times 9.81 is equal to 1962. Okay. And then 19620. Now, we know that sigma Fy is equal to 0. All right. Sigma Fy equal to 0, this implies that the normal force is going to be equal to the weight. We can directly just say that. Then we know there's no other forces in our y direction. All right, if we assume that this is plus x and plus y. All right. We know that there's no other forces in our y direction. There's no acceleration either. So this shows that N is going to be equal to the weight, which is 19620 newtons. This is in newtons. And then, so we found out our normal force. Now we can find the friction force. So friction force Fr is going to be equal to 0.35, which is our mu. So it's equal to mu times the normal force. All right, so mu is 0.35. It's equal to 0.35 times the normal force, which is 19620. So friction is going to be equal to 0.35 times 19620, it is 6,867. So here, keep in mind that our friction force is going to the left and our tension is going to be on the right. This tension force is what is pulling the girder through. What is this tension force trying to overcome? It is trying to overcome the friction force. So for this to have motion, this tension force has to be equal to this friction force or greater. But keep in mind, here in the question, it's not talking about the total force that is being applied by the winch. They only want the tension force in the rope. So we're going to know that the tension force T is going to be equal to the friction force. All right? Because it is just usually a winch, when it's pulling something, it isn't exerting excessive force. It is exerting enough force so that the object is moving. So the minimum required force for this to move is going to be this friction force that should be overcome, which is 6,867 newtons. So the tension force is going to be equal to 6,867 newtons. All right? This is basically how it will be. This is how you would solve any question when it comes to friction. You will draw your free body diagram, all right? After drawing your free body diagram, you're going to analyze your forces, you're going to find your normal force, then you're going to find your friction force to determine your tension or pulling force, all right? Very easy, very straightforward. Don't get too confused about it. Let's do another question so we get a better idea. Now, we have a 20 kilogram block that rests on a horizontal surface and is attached to a mass of 3.5 kilograms by a cable as shown in figure below. So this is our figure here. I'm just going to redraw the figure here one more time. I always like to draw my own diagrams so that I can analyze them in my own way and understand them better. So, oops. So we have a floor here. This is just a floor. This is our 20 kilogram object. Obviously, from the very beginning, I know this is going to have a weight. So this is going to be W, which is equal to mg. I know the mass is given to be 20 kilograms, so I know I can find the weight. I know I'm going to get a normal force over here. And I know that there's going to be a tension force on the right side over here. A tension force T, okay? And I know now I can keep on reading. So the surface and is attached. Why am I not putting a friction force? Because I need to first know if this is a smooth surface or if it has a coefficient of friction. If it doesn't have a coefficient of friction, or if they say it's smooth, I know that there is going to be no other forces applying here. All right. So this block rests on a horizontal. Remember, it says rests, so there's no motion. All right. This means rests, no motion. There's no initial motion, I should say. And is attached by a mass of 3.5 kilograms by a cable as shown. So there's another mass of 3.5 kilogram that is attached with a cable or a wire. The pulley is frictionless and the coefficient of static friction is 0.2. Now, when they say the pulley is frictionless over here, the pulley is frictionless, معناته there is no static friction between the pulley and the wire. That's what they mean. That means here, this is smooth. So as if all the tension is equal between this line and this line. There's no friction force slowing down all of this. So this pulley is super smooth, all right? And since they told us that there is a static friction or a coefficient of static friction of 0.2, so we know now that mu is equal to 0.2. معناته we're going to have a friction force in the opposite direction on this surface. Okay? So I have drawn my diagram. Obviously, just from this information, it's sufficient for me to determine everything. Now, prove that the mass is not sufficient to start the block moving. All right? So they want you to say that this 3.5 kilograms is not heavy enough so that it will pull this. So let's draw a second free body diagram for this mass over here. All right? This is only hanging by a cable upwards. with a tension T. And remember that this tension T is equal to this tension T. So these two tensions are equal. Why? Because this is a smooth pulley and they're connected directly to each other. So any force that is going upwards here is the same force that's pulling it to the right over here. All right? Now, we have drawn the free body diagram for both. What is missing on the right side? We also have the weight, which is equal to mg. All right, W is equal to mg. And the mass over here is equal to 3.5 kilograms. So let's call this M2 and call this M1. So this is M1 and this is M2. Okay? So let's start doing the analysis now. Let's start doing the analysis. So first things first, let's look at our right side, our free falling or hanging mass. We know that sigma Fy, so sigma Fy is equal to 0. All right? This is for mass 2. Okay? Sigma Fy is equal to 0. So the tension force T has to be equal to the mass G, mg, or the weight, yani. All right? Why? Because again, if we are gonna assume our positive direction is this way. So this is the positive directions plus y plus x. Okay? This, in other words, we can write it as is equal to T minus W. All right? But I can instantly see that T is equal to W because there's only one force going up and one force going down. So they have to be equal to each other. All right? So T is equal to W. Tamam? We know that there's no acceleration up and down. Why? Because it already says in the question that the mass is not going to be sufficient, and it did not mention, it mentions that the block as well is at rest, so there's no movement. If there was acceleration, this is not going to be equal to 0. But since there is no movement, they are saying it is not sufficient, we know that this is hanging still, it is not moving. All right? So the tension T is going to be equal to, let's find the weight. The weight is mg. We know that the mass is 3.5 kilograms, so it's going to be 3.5 times 9.81. Did they mention in the question what to take? Nope, they didn't, so I'm just going to assume it as 9.81. So W is equal to 3.5 times 9.81 is equal to 34.335 newtons. So we know that our tension force is also going to be 34.335 newtons. Okay? So we have found our tension force. So remember, this tension force is the same as the tension force over here, all right, on the other free body. Because they're the same, we can use the same number for this analysis now of the left side. First, let's do our sigma Fy. We know that there is no motion. Now this is for M1. Okay, so Fy is equal to 0. That means that the tension or the normal force is going to be equal to the weight. Again, there is no motion in the in the vertical axis. Then, so normal force is equal to the weight. We know that the weight W is equal to mg, so it's equal to 20 kilograms times 9.81, which is equal to 20 times 9.81, 196.2 newtons. All right. So we know that N is going to be equal to 196.2 newtons. All right. So we found our normal force. We can now find our friction force as well. So our friction force now is Fr is equal to mu times N. All right. Mu times N. So it's equal to, what is our mu? Our mu is given to be 0.2. Our mu S actually, this is mu S, mu of static friction. All right. Remember, we use mu S when we want to know if the force is strong enough to either overcome or if it's just large enough so that it will, or as if it's too small, that means whether the friction force is large enough or small so that the tension force is large enough to overcome it, basically. So 0.2 is our mu s, 196.2 is our normal force. All right, 196.2. So our friction force is going to be equal to 0.2 times 196.2. This is going to be 39.24. 39.24 newtons. Now, how do we know? We compare our tension force T, which is equal to 34.335 newtons, with our friction force Fr, which is 39.24. 34 is smaller than 29, so if the friction force is larger, that means no motion. All right? If the friction force is less, there will be motion. If it's larger, there is no motion. The question also says, what is the additional mass required to start the motion? What they mean is the mass for M2, what should be the weight of it so that it can start moving? So here we're going to reverse engineer this. So we know that the tension force, we know that T needs to be greater than or equal to Fr so that there's motion. So the minimum tension has to be equal to the friction force, which is equal to 39.24 newtons. Okay, this is the minimum tension we need so that there will be motion. For motion. Okay, the minimum required tension is 39.24. So if we reverse engineer this here, we know that tension is equal to the weight of weight 2. Let's call this weight 2 and weight 1 so that there is no confusion again. This is for mass 2. This is for mass 1, W1. Okay? So we're going to reverse engineer this. We're going to work backwards. So the tension force now we know is 39.24, and we know that tension is also equal to mass 2, or W2, I should say. And we know that W2 is equal to mg. So we know that tension is also equal to mg. All right? Our tension force is equal to mg. Again, we're not doing anything new. This is just, we're going backwards. So we know, let's do it in an easier way so you guys will understand. So it's equal to W2. Tension has to be 39.24, therefore W2 has to be equal to 39.24. All right, newtons. We know that W2 is equal to M2 times G. Again, this is M2. We're talking about mass 2. All right? If we rearrange this equation, we're going to find that M2 is equal to, how do we rearrange it? We divide both sides by G. This G and this G will cancel. And then we will be left with M2 is equal to W2 over G. All right? We know that W2 is 39.24 newtons. And we know that G is 9.81 meters per second squared. Okay? So M2 is equal to 39.24 divided by 9.81, which is 39.24 divided by 9.81 is equal to 4 kilograms. So the total mass on the right side has to be 4 kilograms at the very least, so that this will be able to overcome the friction force. So how much additional mass we need? We have 3.5 kilograms, all right? So I'm going to call this M2E, okay, as an extra. So M2E, okay, right? This is W2E. This is tension E, so this is the extra tension. That's the only reason, so that there's no confusion between this W2 and that W2. Again, this is TE has to be equal to the friction force. TE has to be greater than or equal to the friction force. All right? So M2E is equal to 4 kilograms. Our original M2 is equal to 3.5 kilograms. So the extra mass here, how are we going to do it? We're going to just do M2E minus M2, which is equal to 4 kilograms minus 3.5 kilograms. So we're going to need an extra of 0.5 kilograms so that it will be moving. Is this clear? Does anyone have any questions about what I've done so far? So this is our additional mass. All right, additional mass required. Clear? We move on? Okay. I'll do one more friction problem, and then I'm going to move on to energy. And then so we have this question over here. Each of the two blocks in figure 2 below has a mass of 10 kilograms. So we have two blocks, each with a mass of 10 kilograms. And the coefficient of friction between all surfaces is 0.3. What does that mean? So first we have this surface, which is the top of the cube. This surface has mu of 0.3. And this surface, which is the floor, the coefficient of static friction, or just the coefficient of friction, is also 0.3. Determine the force Fp. This is our force Fp over here. This is Fp. Required to pull the block from under the other. So we're trying to remove this block. If you notice, there's a wire here. There's a wire over here that is holding the top block. So the top block is not going to move. But the bottom block is going to move to the right side once we have an enough force P. Okay? Again, very simple and straightforward. Very simple and straightforward. We are going to just draw the free body diagram of the bottom block, the one that is that we are trying to move. Okay? Now, let's draw it. Okay, so this is our block. This is our block. We have this block that is sitting over here. Tamam? We have the weight of the block, W1, which is the first block. Then we also have the weight of the second block applied as well. All right? I'm going to use a different color for the second weight. So we also have W2. All right? Why? Because there is a weight that is being applied to it, or if it is easier for you guys to see, there's the weight of the other one is going to be applied over here. W2. Okay? This is the weight of the second block of this block. Okay? And this is the weight of this block. Remember that both W's are equal to mg, mg. And the masses are the same. They're both 10 kilograms, so m is equal to each other. All right? Now we can look at the normal force. The normal force is going to be from the surface upwards. There's only one normal force. Okay, because we're looking at only one block. This is our normal force. And we have the force, the pulling force over here to the right, Fp. Remember, this is going to be my plus x and plus y. Okay. Now, what do we have left? We have our friction force. So the first friction force we're going to have is at the bottom with the surface. Okay. This is our friction force 1. Then we're going to have another friction force up here. Why? Because we have a friction force that is coming from the top block. Because remember, they never said this is a smooth surface. They said that between all surfaces, there's a coefficient of friction. So there is roughness between all the surfaces. معناته هني there's also going to be mu. So this is FR2. And remember that this FR is equal to mu times it's going to be mu times the normal force. But there's one thing I need to, I will show you about FR2 in a bit. If we draw the top box now, then, so we finished drawing the bottom box, okay? This is now the top. So this is the top, and this is the bottom. Okay? The top box is on top of, not a flat surface, actually. It's on top of the lower box. Okay? We know that the friction force over here, at the bottom, for the top one, by the way, it's going to be in the opposite direction, but don't get confused by that. Okay? It's going to be in the opposite because, remember, friction is opposite to the motion. But again, just so there's no confusion, I just want to explain the concept. The friction caused by this one depends on the normal force of the top box. Okay? Depends on this normal force. So this FR1, all right, depends on the normal force for the top box only. And remember, the top box only has the weight of the top box acting on it. The weight of the bottom one is not applying, right? So the weight is W2 equal to mg. All right? Again, let me repeat. So this is for the bottom box because we have the weight of the up and the down acting on each other. And there's a friction up and down as well. For the bottom box, for the top box, sorry, there's a normal force. There's no force being applied left or right. There's only a friction force which is being applied to the bottom of it. All right. The reason, by the way, the friction force is going to be the opposite, so you guys just understand the concept. The actual friction force is going to be here. Why? Because the normal force or the tension force, there's a tension force in the cable in this direction. All right. Remember, there's a cable that is holding it still here to the wall. So the friction is going to be opposing that so that the tension and friction are equal to each other. And then that is why the friction is going to be, this is when it's acting on the top. But when we're acting on the bottom, it is going to be the opposite of the motion of the bottom. And the bottom one, it is going to be moving in that direction. So the motion here, the motion is going here. That we want to achieve the motion towards the right. This is for the top box only. But what I want you guys to look at here is that the friction force here is going to be different. This is FR2. It is going to be different than FR1. Why? If we want to find our friction force here, how are we going to do it? So for top, okay, now we're going to do the analysis for top to find the first friction force. We know that sigma Fy equals 0 معناته N2 is equal to W2. All right. Again, this, don't get confused. This is N1 and this is N2. Okay. So N2 is equal to W2. معناته, we know that W2 is equal to mg. We know that the mass is 10 kilograms times 9.81 for the gravity. So W2 is equal to 98.1 newtons. All right. Because we know that the mass is 10 for both, okay? So N2 is going to be equal to the weight, which is 98.1 newtons. We know that friction, FR2, is equal to mu times N2, okay? Since mu is the same everywhere, mu is the same, we know that mu is equal to 0.3 everywhere. So it is equal to 0.3 times N2, which we found earlier, is 98.1 newtons. Okay, so this, we can find now the friction force 2 is equal to 0.3 times 9.81, or 98.1, sorry, is 29.43 newtons. So we found our friction force, and this is the only thing we need to analyze FP from the top box at least. So for the top, we found out the analysis of the friction force 2. Now, for the bottom, okay, We are going to do the same exact thing first. We're going to do sigma Fy equals 0. All right. Let me just copy paste this down so we can work with it. So this is what we have for the second one, for the bottom. Okay. We know that we have sigma Fy equals 0, obviously. And then, so we have, let's analyze it one by one. So sigma Fy is equal to, what do we have upwards? The N1 plus N1 minus W2 minus W1, because these are both pointing downwards, all right? And we know that W2 was 98.1. We can find that W1 is also equal to 98.1 because it's the same mass. So 10 times 9.81, W1 is equal to 98.1 newtons, okay? So if you notice here, we're going to have two weights we have to consider for sigma Fy. So sigma Fy is equal to this, and this equation, which is, remember, again, equal to 0. So N1 is equal to, or N1 minus W2 is 98.1. 98.1 minus W1, which is also 98.1, is equal to 0. So now, if we take both of these to the other side, let's simplify first before taking them to the other side. So N1 minus 98.1 minus 98.1 is equal to minus 196.2, which is equal to 0. We take this to the other side. We will find out that our N1 is equal to 196.2 newtons. Notice how here the normal force is not the same as the normal force we found earlier. All right? Let me just highlight this. So this N2 is different, okay? This normal force that we found here is different. This one is not the same as N1 that we found earlier. Okay? Now we are trying to find N1 to find the friction force, the red friction force that is being between the ground and the box. We already found FR2, we just need to find FR1. So FR1 is going to be equal to mu times N1. يعني FR1 is going to be equal to, mu is 0.3 between all surfaces, and N1 is 196.2 newtons. So FR1 is equal to 0.3 times 196.2 is going to be 58.86 newtons. Okay? So now that we have found our friction forces, we know that this is FR1 and FR2, we found it earlier on. We can determine our force FP so that determine the force FP required to pull one block from the other. So basically we require the minimum FP force, all right? How can we find the FP force? Again, sigma Fx equals 0. So that, again, if I copy paste this down so you guys can see what I'm doing. It's not actually sigma Fx equals 0 because there will be motion, but it is because we're talking about the minimum force, it is basically just as it's about to move. So you could say sigma Fx equals 0, but so that there's no confusion, when we say sigma Fx equals 0, معناته what we mean is the friction forces on the left have to be equal to the Fp. So it is going to be, if we're following the same rule, Fp minus FR1 minus FR2. Why is it minus? Again, because our plus x direction is to the right. So Fp is going to be to the right. And our friction forces are to the left. So we need to find the minimum possible force so that Fp is going to be pulling the box from the bottom. All right? So now we could just substitute all the values that we have found for Fr. So Fp is equal to, or FP minus FR1 is 58.86 minus 29.43 is equal to 0. FP is equal minus, let me just simplify, minus 58.86 minus 29.43 is minus 88.29 equal to 0. So our FP is going to be equal to 88.29 newtons. Again, quick recap of how I did all of this. The very beginning, we have two blocks, all right? So we're going to analyze and draw a free body diagram for each block by itself. Then we're going to analyze each block by itself. The top block, it is between two surfaces. Then we have a surface at the top here. There's a surface and there's a surface at the bottom here. Okay, so it has two surfaces and each surface is going to have its own friction value. So there's a friction value here and there's going to be a friction value over here. All right, that's the first thing. That's why we have FR1 and FR2. Then we have the weights. We have two weights. We have the weight of the top box on top of the weight of the bottom box. So there's two weights acting on the bottom box. There's W2 and W1. And then we have our FP, which is given, and then the normal force, which is one force from the surface of where this is acting on. For the top box, we have the same exact concept. We have the normal force from the surface of the bottom box. Okay, so this is the bottom box. Okay, we're going to have the friction force in the opposite direction because remember, the top box is trying to be pulled onto the left. So the motion technically of the box is to the left, not to the right. So the friction force is going to be opposite on the top box. W2, it doesn't matter, by the way, the direction, because the solving is going to be the same even if you get the direction wrong for the top box, not for the bottom. But anyways, then you have the weight of only the top box that is acting and the normal force 2, which is depending on just the top box by itself. It's from the surface of the bottom box. Then, now we can do the analysis here to find FR2. We do our sigma Fy equal to 0 to determine our N2 value. And once we determine N2, we can find the friction force. Once we determine our friction force, now we are done with the top box. We look at the bottom box and start our analysis there. Again, sigma Fy equal to 0. Yani the summation of forces along the y-axis is equal to 0. We have N1 in the y. We have minus W2 and we have minus W1 going downwards. So N1 going upwards. That's why it's positive. W2 and W1 are going downwards. That's why it's negative. They're all equal to 0. And then we just solve the equation to find N1. Once we find N1, we can find the friction one because friction is just mu times N. We know that the coefficient of friction is the same for all of them. We multiply, we find our FR1. Now that we have FR1 and FR2, we can do our sigma Fx is equal to 0, basically meaning the summation of forces along the x is going to be equal to 0, as in we are looking for the very bare minimum force before the motion even, like when the motion is just about to start, so that it will be pulled right out of it. So in other words, we could just substitute for sigma Fx. We know that sigma Fx is equal to Fp, so sigma Fx, which is the summation of forces. Yani basically all the forces added up is going to be positive Fp minus Fr1 because it's to the left and minus Fr2. Okay. And then we just plug in all the values we have and we can solve for Fp. Tamam? Is this clear, everyone? Any questions before we move on to energy? Okay. Let's take a 2-minute break. I'm just going to grab me some water. 2 minutes break, and inshallah we'll start with energy. All right. Okay, so now we're done with forces. You guys should have a good idea about what all the forces are, how to analyze forces and moments in general. Let's talk about work and energy. Okay, so energy can come in many different forms. It can be kinetic, potential, which we will talk about and focus on mainly. It can also be sound, it can be chemical, it can be nuclear. There's a lot of type of energy in the word. Energy is طاقة, اللي هي الطاقة. إنزين? So how do we define energy? What is the idea of energy? Energy is basically the change, or when there is a work being done, so that there is يعني مثلا if you're applying a force and it's causing it to move, so there's energy in that object that's causing it to move. So the energy and the work is going to be dependent. So the energy is basically simply work done. All right, so this work done, it depends on the force, and the distance it is moving, or the distance of it that it is moving. Okay, so this is what energy is basically based upon. It is based on the work done, which the work is going to be based on the force and the distance. And simply the work done, W, work done, is equal to force times distance. Okay, so this is the applied force, and this is the distance moved. All right, this is the simple uh, explanation of the work done, which is also equal to the energy being transformed. All right. So if we look at a simple object that is being moved, that is being pulled into this direction, all right, with a specific force, all right, and let's say it moved 10 meters, all right, and the force is 30 newtons. Okay. So to move this object here, 10 meters, all right, we're not looking at friction and all of that. We're looking at the total force that is just being applied. The energy you have to put in, or the work that is being done to this, is going to be equal to 30 newtons, the force, times 10 meters. So the work done is going to be 300 joules. Joules is basically the unit for energy or for the work that is being done. If you notice that joules is basically equal to Newton meter, so joules is the same as Newton meter. It's not the same as torque. Don't confuse between torque. Torque is just given in Newton meters. Joules is talking about energy now. All right. Torque or moment, don't think about that. We're talking about energy or work done. All right. So the way you will do it is that simple. You'll just look at the force that is being applied, and you will see the distance that it has been moved, and that is going to be your work done. This is what the basic of the basic work done. Sorry, this is the basic formula for the work done and for energy. Let's say that there is no movement. Let's say for the same example, okay, block doesn't move. All right, that means our work done is going to be equal to 30 newtons times 0 meters, because it's not moving. There is no distance that it is moving. So since it does not moving, that means there is no work done. So work done is going to be equal to 0. So work done, there is no work that is being done. Okay? That's it. That's how simple it is. This is how you'll always find the work. It will always depend on the force of movement, the applied force, I mean, and the distance that is being moved. So again, energy is equal to this work done, but there are different types of energy. And how can we determine those? So first of all, there's two types of energies you guys really need to focus on. There's the gravitational potential energy. Potential energy. Or usually for short, they write it as PE. Okay? This is potential energy. What does this mean? This is the energy, all right, of an object when you're required to lift it upwards, or if it's falling downwards or along those lines. In other words, إذا عندنا block, all right, and it is going up, all right, we're moving it, we're lifting it up, so we're applying a force upwards. Then here, this is what we call it having a specific height here. So let's say this height, this is 0 meters, so it's not moving, and the box is moved all the way up to here. So this is our distance that is being moved, all right? So here we can simply say that the work done, or the energy to move it up, remember work done is simply equal to energy, is going to be equal to force times distance. All right? Force times distance. But remember, there is a weight for this box, mg, right? Or W, which is equal to mg. And we know that the force F to lift this has to be equal to W. صح ولا لا؟ لأن to move this force upwards we have to overcome this weight of it. إذا كان الأوبجكت ثقيل ما بنقدر نشيله. إذا كان خفيف we can lift it. So if it's heavy it's difficult to move up. But if it's light enough we will be able to apply enough force to lift this object. So in other words the force is equal to mg. All right? mg, just the weight. So if you notice now, if we apply our work formula, our work done formula, it is equal to force times height, or we know that force is equal to mg. So it is equal to mgh. This is what we know as potential energy is going to be equal to, because remember, energy is simply just work done, and potential energy is talking about height when we're going up and down. All right. So when we're basically trying to relate it to the gravity that is being applied to it. So potential energy is going to be equal to mgh. Very simple, very straightforward. I believe this is also in the formula sheet, so there's no need for memorization. This is just so I can explain to you the concept of gravitational potential energy. Okay? So energy, the potential energy is going to be mgh. So what we can basically say is that this box now is storing potential energy. زين يعني this box, because it is at a specific height, it has a specific potential energy. If we look at a very basic example, زين, let's say you have a mass of an object, all right? This is a mass m. M is equal to 2.5 kgs, okay? And you are going to have to lift this mass to put it on top of a table. And then there's a table over here. Okay? You want to lift this mass to put it on this table. Okay? This table is, let's say, 2 meters high. Very large table. But for example, let's say it's 2 meters high. Okay? All you're going to have to do, how can we find now the energy? How much energy does this, the way they will ask is how much energy does this mass gain? Does this block gain? Yani how much energy will this have? How much potential energy will this gain? How do you find that? Again, simply PE is equal to mgh. We know the mass is 2.5 kilograms. We know the gravity is 9.81, or it will be given in the question. And we know that the height is 2 meters. So simply you just multiply all of this together. So 2 times 2.5 times 9.81 is going to be 49.05 joules. Again, remember that energy and work done is always going to be in joules. Tamam? So this is basically how it is for potential energy. Remember, potential energy means vertical height. Okay? Every time an object is going higher up, it is gaining more potential energy. Every time it is going down, it is losing potential energy. All right? So if it is going up, gaining potential energy. If it is going down, it is losing potential energy. That is the whole concept of potential energy. All right. Now we have also another object or another formula or another type of energy, I should say, which is the kinetic energy. And usually this is written as Ke, or sometimes they write it as Ek, and for potential energy, sometimes they write it as Ep. Sometimes, okay? It depends on the way they write it. It doesn't matter as long as you understand the concept. Then, kinetic energy is basically the movement of an object left to right. Okay, so if an object is moving to the right or if it's moving to the left, all right, this movement is kinetic energy. So how much you are moving an object to the left and to the right is basically called the kinetic energy of that object. And then kinetic energy, the equation of it is half mv squared, where v is the velocity of object and m is the mass, which is very clear, يعني mass. Okay? So v is the velocity, or in simpler terms, speed, then of the object. تمام? So if you notice, every time your speed is higher, you're going to have higher kinetic energy. If your mass is heavier, you're going to have higher kinetic energy. So the kinetic energy depends on the mass and depends on the velocity of the object in each direction. Let's take a simple example. Let's say, what is the kinetic energy of a ball? We have a ball, okay, that is being thrown in this direction, all right, with a speed of 22 meters per second. And let's say the ball has a mass of 200 grams. And then, remember, when you have the mass in grams, you need to convert it into kilograms. Remember that 1 kilogram is equal to 1,000 grams. And the way you will do this conversion, so M is equal to 200 grams times, we need to cancel the grams, so the grams will be down. And we want it in kilograms, so kilograms will be up. 1 kilogram is equal to 1,000 grams. So you'll put 1 up and 1,000 down. You'll notice here grams and grams will cancel. So you'll remain with 200 over 1,000 kilograms. Okay, if you just do this multiplication. So this is basically equal to 0.2 kilograms. This is the first step you will do. Make sure that always your mass is in kilograms, and your velocity always has to be in meters per second. Okay, again, so this velocity of the object is in meters per second, and the mass has to always be in kilograms for you to get the unit of joules. All right, remember, energy is always going to be in joules. So this is it, half mv squared. And that's all we're going to have to apply here. So we have the mass. So kinetic energy is going to be equal to half m, which is 0.2 kilograms, 22 meters per second squared. And then let me put it with units so that I can also explain to you how the units will work. So this is going to be 0.2 kilograms. And this is meters per second, all of it squared. And then if we simplify this, this is going to be half times 0.2 kilograms. And now we have to square this. So 22 squared is equal to 484. Meters will become squared and seconds will become squared. And then, again, I'm just going to explain the units here. There's nothing to memorize here. It's just an explanation of the units. So this is going to give us, remember, this is half times 0.2 kilograms times 484 meters squared per second squared. In other words, if we simplify all the numbers, it's just half times 0.2 times 484, which is 48.4 kilogram meters squared per second squared. If you remember, force is equal to mass times acceleration, right? So this is kilograms meters per second squared, right? So this is what force is. If we do force times distance, it is going to be kilograms meters per second squared times meters. So it's equal to kilogram meters squared per second squared. If you notice here, this unit is the same as this unit, all right? And these are both equal to joules, 48.4. Remember, this equation is work done, all right, which is also equal to energy, okay? Work done is force times distance, which is kilogram meter per second squared times meter. So it's kilogram meter squared per second squared. This is the same unit again. So this is going to be in joules. This is why you always have to change it to kilograms and to meters per second when calculating. All right. The most important thing here to know is just do that. Make sure the conversions are being correct. Velocity is in meters per second and the mass is in kilograms. So that's it. These are the two types of energies you have. You have the kinetic energy, all right, which is usually movement from left to right. And then we have the potential energy, which is the movement up and down with respect to gravity. Then, there's one more thing I want to go over, which is power. So we have done work done. We understood what work done is. Work done is simply just a quick recap. So work done is equal to force times distance, where this is the applied force and this is the distance moved. Potential energy is equal to mgh, where this is the height and m is the mass. So if I just mention these, this is applied force. This is moving distance, distance moved. M is the mass for potential energy mass, and this is in kilograms. Okay, applied force here is going to be in newtons, and this is in meters. G is gravity. Everyone should know this by now. This is just acceleration due to gravity, which is in meters per second squared. And this is the height, which is in the height, which is in meters. And now we did the kinetic energy, which is equal to half mv squared, where this is the mass again in kilograms, and this is the velocity in meters per second. Okay, so we now know the work done, the potential energy and the kinetic energy. Remember that energy and work done is the same thing. Now let's talk about power. So power is how much energy you are applying over a specific amount of time, or how much work done you are doing over a specific amount of time. So let's, for example, it's going to be WD over time, all right? This is time in seconds. That's it. This is what power is. Or you can also say it's the potential energy over time, or you could say it's the kinetic energy over time, depending on the type of question, because remember, power is simply work done over time, or you could say it is energy over time. Yani, if we are looking at the very first example we did with this block over here, okay? If we're looking at this example, insane. So the example was, we have a block, all right, M, with a mass, a specific mass, and it is moving over here with a specific force that was 30 newtons, I believe, and we said the distance it covers is 10 meters, okay? What does work done over time means? It means how much time does it take for this to move the distance 10 meters given this given force. So let's say, for example, it took, I don't know, 5 seconds. It took 5 seconds to move that much. So the power is going to be equal to the work done, which is force times distance, divided by time. Or it's also equal to 30 newtons times 10 meters over 5 seconds. That's basically how you would apply it. So if we just do this calculation really quickly, we're going to get power is equal to 60 joules per second. Because remember, work done is in joules. Force times distance is work done, which is joules. And time is per second. This is also known as watts, 60 watts. So joules per second is also known as watts. Okay, this unit is the unit for power. And that's pretty much it for all of energy and work. It is very straightforward. Again, there's no confusion at all here. What they will do is they're going to give you, we're going to look over a few questions, but the ways they will give you questions is they might give you power, they might give you the distance and the work, and they will tell you, for example, and the time, and they'll tell you, for example, find the force. Or they will give you force and distance and power, and they will say, find the time, or something like that. Yani they're going to give you some parts of an equation, and they will tell you to find the remaining. Let's look at a few examples so we can understand. But before we move on, does anyone have any questions about what I have explained so far? Okay. So let's take this example, a simple example. A person of mass 70 kilograms. So we know that the mass is 70 kilograms. M is 70 kgs. Okay. Runs up a flight of stairs with a vertical height of 5 meters. See, when you read vertical height, you're going to instantly know that there's going to be potential energy. لأن it's moving vertical. The electrical part is not included in your exam. No, I already confirmed this with Ustad Isa, the coordinator. Okay, this is going to be the last concept. Work, energy, and power is going to be the last concept, but mechanical energy and mechanical power. We're not talking about electrical power. Electrical power will be for the second half of the semester. Up to the midterm, it's only up to this. Okay. So again, a person of mass 70 kilograms runs up a flight of stairs with a vertical height. So we know that there's potential energy because we're moving vertically of 5 meters. So we know that H is equal to 5 meters. If the trip takes 7 seconds to complete, calculate the person's power. So what are we trying to find? We're trying to find power. All right. We know that time is 7 seconds. First things first, we know that power is equal to energy over time. We know here the energy they're talking about is potential energy over time. And we know that potential energy is what? mgh over time. So now you have your equation and you're just going to plug in values. So the 5 meters is your height. So this is your height. G is a constant that we already know. 7 seconds is your time. Okay. And 70 kilograms is your mass. Okay. And G we know is a constant that we already have. So you're just going to plug in all those numbers. So 70 times 9.81 times the height of 5 meters all over 7. And this is how you'll find your power. So power is going to be equal to 70 times 9.81 times 5 divided by 7, 490.5 joules per second or 490.5 watts. Tamam? That's how you will solve a question for power. Let's look at another question. Okay, this is a good question. A lift motor has to move a fully laden lift 4 meters between floors. So a lift goes up and down, all right? So we know that there's going to be upwards and downwards motion in general between floors, and it has to lift it 4 meters. So we know our height. This is our height h. H is equal to 4 meters. And we know our time t is equal to 1.5 seconds. Remember, as long as the units are in meters and seconds, you can go ahead and move on. The lift has a mass of 1,850 kilograms. So this is your mass. Calculate the weight of the fully laden lift. So how do we calculate weight? Very simple. Weight is mg, which we know from early on. So it's going to be 1850 times 9.81, which is 1850 times 9.81 is 18148.5 newtons. Okay, that is our weight. Very easy, very straightforward. Part B says, what is the upward force in the cable when the lift is moving at a constant speed? So we're talking about force. Remember, if we draw the free body diagram very quickly, this is our lift. There is going to be a force F upwards and the tension force in the cable. And we have our weight downwards. Sigma F Y equals 0. معناتها F is going to be equal to weight. So the force is simply equal to 18148.5 newtons as well. Tamam? So we know that the force here is 1814.5 newtons, like we did earlier a lot. And now the question is saying, what is the work done by the motor? Again, very straightforward. We know that work done is equal to force times the distance moved, or in this case, the distance is the height. So force times the height in this case, because here they gave us a distance of 4 meters or a height of 4 meters that it is moving. Okay. So we already know what the force is. We know what the height is. This is equal to, the force is 18148.5 times the height was 4 meters. Yes, 4 meters. So it's equal to, you just multiply this by 4, and it's going to be 72594 joules. Remember, we're dealing with work, so work is in joules. All right. And now the last part says, what is the minimum power of the motor to raise the lift at a steady speed? For the minimum power we need is supposed to be equal to the minimum work needed for this force. So power is equal to work done over time. What is work done? We have it. We already found it from the previous question. And what is time? It's given to be 1.5 seconds. So we directly just plug this in. 72594 joules over time, which is 1.5 seconds. So it's equal to 48396 watts. All right, joules per second or watts. So this is the minimum power the motor requires so that it can move the lift upwards, basically at a steady speed. And that's it. That's how you would solve any question for power and energy. Let's do a few more. So here the question says, how fast is a trolley moving if it has this much kinetic energy? All right. How fast is a trolley moving if it has this much kinetic energy? So how would we do this? So kinetic energy is equal to half mv squared. And we know that the kinetic energy is equal to 180.5 joules. Tamam? So now we need to solve for V. Remember from math transposing? This is the same exact idea. This is how you would solve for V. So if we do the transposing, you're going to notice that. And if we're putting V as our subject, let's look at just this part without numbers. I want to solve this with transposing so you guys can be familiar with the math as well. So kinetic energy, we're going to multiply both sides by 2. All right, so we're going to multiply both sides by 2 over here and here. So we can cancel the 2. And then we're going to divide by m on both sides. So we can cancel the m. So it's going to be 2ke over m is equal to 2 over m times half mv squared. If you notice, the m and the m will cancel, the 2 and the 2 will cancel. We will be left with 2ke over m is equal to, again, no confusion. All I did here was multiply by 2 over m times kinetic energy. And then it is equal to v squared. When you have squared on one side, remember, we're trying to find the velocity. The question is, how fast is the trolley moving? So we're trying to find velocity or the speed. So here, the mass of the trolley is 4 kilograms, by the way. Okay. So the mass of the trolley is 4 kilograms. So if we want to keep solving here, to get rid of a square, we need to do square root on both sides. And then here, the square will cancel with this. So we'll get a final equation of V is equal to the square root of 2 times the kinetic energy divided by mass. If we plug in all our numbers now, V is equal to the square root of 2 times, what is our kinetic energy? 180.5. Divided by, what is our mass? Our mass is 4 kilograms. Plug this all into the calculator. So it's going to be the square root of 2 times 180.5 over 4. You're going to get 9.5 meters per second. Remember, velocity's units is in meters per second. All right? Now, there is another concept that I didn't really go over, but there's the concept of conservation of energy. What does conservation of energy mean? Conservation of energy. Then, let's take a simple example so I can explain this concept. Then, we have a ball on top of a table. Okay? We have this ball that is on top of a table. Okay? This ball is rolling in this direction until it falls off. So eventually it will fall off and hit the ground over here. Then, so this ball is rolling and then eventually it will fall off and it will hit the ground over here. Okay? So here, initially, then this ball had some potential energy because it has a specific height from the ground, right? So when it has a specific height from the ground, so a height h, okay? If it has a specific height from the ground, معناتها it has some potential energy. When it's falling now, okay, when it's falling, this potential energy is being converted. So this is being converted into kinetic energy conversion. Or sometimes they say transformation. How so? لأن now if you notice this potential energy at beginning, it was to up, okay? And a better way to actually draw this would be if it's a slanted height so you guys can see it better. So let's say it is at a curve like this. Okay? So this ball at this point had some potential energy. And then with time, it is falling. Obviously, it will fall due to gravity. The force of gravity is pulling it down, so it's falling. So from here to here, the energy is changing from potential into kinetic. All right? So initial phase, or we'll call it phase 1. And then the final phase, we'll call it phase 2. If you notice at the very beginning, it was at rest. So for example, someone was holding it in place, and then no one was moving the ball. Or there was, for example, a gate over here that was holding it in place. And then the gate suddenly opened. All right? So this is a gate. And then suddenly this gate was opened. Okay? نفس الالعاب, you know, when you go and play those basketball games where there's like a lot of balls, and once you pay, يعني with the card you swipe or whatever, the cage is opened and the balls start falling. Same exact idea. So as soon as this gate opens, so before it's opening, this is the initial phase. Kinetic energy here is equal to 0. So I'll call this kinetic energy 1. It is equal to 0 initially. But there is some potential energy because these balls are at a specific height from this ground that we are identifying. Okay? Once the gate opens, then these balls are going to fall down, transforming or converting all the energy from potential into kinetic energy until it reaches the ground. And here, the potential energy now of 2 is equal to 0. So what does this mean? The conservation of energy theory basically says that the kinetic energy 1 plus the potential energy 1 is going to be equal to the kinetic energy 2 plus the potential energy 2, where 1 is the first phase, the initial phase over here. So this is P1 also, and this is K2, KE2. So the initial phase energy, energy initial has to be equal to energy final. لأن what the law says is energy cannot be created nor destroyed. You cannot create energy, you cannot destroy energy or create energy, but you can transfer or transform energy. And the energy is always going to be transformed into another type of energy. It cannot just disappear into the air. So the conversion or conservation of energy is going to be basically this formula. All the energy in the initial phase has to be equal to all the energy at the final phase of a specific object. In this case, we know that kinetic energy 1 is equal to 0. And we know that potential energy 2 is equal to 0. So we know that here potential energy 1 is equal to kinetic energy 2. In other words, we know that potential energy is mgh is going to be equal to the kinetic energy, which is half mv squared. If you notice here, okay, here, since there's a gate, velocity 1 is equal to 0. But here, since there's movement, so here there's a velocity that is equal to something, a number. I don't know what the number is, but there's a random number. Let's say 5 meters per second. Okay? Same thing for the potential energy. Potential energy here, we had a height. So at this point, there was a specific height. So let's say height was equal to I don't know. We don't know what the height is, okay? Let's keep the height as a random height. Then I will tell you why I'm not going to give a number to height. But it has a specific height here, h1. h2 over here, we know h2 is equal to 0. Because there's no velocity v1 is equal to 0, remember it's half mv squared. So half m times 0. Yani ke1 is equal to half mv1 squared. But since v1 is equal to 0, this all is going to be equal to 0. Same thing with potential energy 2. It is equal to mgh. But since the height is equal to 0, the potential energy is going to be 0. Tamam? This is the whole idea of conservation of energy, and this is the whole idea of how to apply your kinetic and potential energy formulas. So why did I put this height 1 as no number? Because we can solve now for this height if we are given the mass of the ball. Even if we're not given the mass of the ball, we can solve for this height. And I will show you how now. Since we are just given the final velocity, we know that this v over here, this velocity over here is equal to v is equal to 5 meters per second. صح? This is our v2, remember. This is v2, which is at the bottom here. v2, which is equal to 5 meters per second. Okay? So we know that this velocity is 5 meters per second. Let us now try to find the height, h. Again, transposing from math. This is good to practice your math again. So how can we have h by itself on the left? We have to divide both sides by mgh. So we're going to have to divide by mgh here, or mg, sorry, and divide by mg on this side as well. So we are going to see that mg and mg will cancel over here. And if you notice on the right side, the m will cancel with the m as well. So we know that h is equal to half v squared over g. Or if you want to write it, you can write it as v squared over 2g. Okay? This is, how did we come up to this equation? Because of the conservation of energy. Because the kinetic, the potential energy, the total energy initially has to be equal to the total energy finally. So now we can just solve for h. H is equal to, we know that v squared is, we know that v is 5, so it's going to be 5 squared divided by 2g. So it's equal to 5 squared. G is 9.8. 1. Okay, so it's going to be 25. 5 squared is 25 over 2 times 9.81 is 19.62. Therefore, the height is equal to 1.274 meters. Okay, one thing again I want to clarify here. If you look at the units, so h is equal to v squared. It is meters per second squared, so it's squared over 2 times meters per second. Okay, meters per second squared is going to cancel with meters. Second squared is going to be cancelled by, oh, this is meters per second squared. Second squared is going to be cancelled by second squared. All right, there's no 2 here. This 2 is a constant. So it's equal to meters. So that's why we got our height in meters. If you want me to clarify this a bit more, this is meters per second, all divided by, squared, sorry, by meter per second squared. The way I usually solve if I have this, and this double fraction, I take the close ones together. So I'm going to take this and this together and multiply them. And the further apart, I'm going to take them and multiply them. Okay, so the further apart ones are going to be up and the ones closer together are going to be down. Okay, so it is meters squared second squared divided by meters times second squared. If you remember from your math again, algebraic fractions, second squared and second squared will cancel completely because it's 2 minus 2, which is 0. So it's s to the power of 0 is equal to 1. And then you have here again the same thing, 2 minus the power of 1 over here. So m2 minus 1, which is simply equal to meters. Okay, this is just to explain to you how we are coming to these units. This is why you should always make sure you are always having the correct units initially, so that when you're solving, you will reach the proper solution. And we are done with everything up to energy. We are done with all of the physics courses. Anyone has any questions? Inshallah, tomorrow we will be doing the